minus the p square over 2m minus pf square over 2m. Yeah, but for interacting fermion, it's some quantity that measure roughly the distance to the, sorry, let me write like this, equal to Vf times P minus Pf. So for the Landau's quasi-particle, the assumption is that the energy is equal to 0 if the momentum is equal to Pf, and is linear if I go away from Pf. And if I go away to the inner direction, I excite not particle but a hole. And hole has energy that is also looks like this formula with the opposite sign. Okay, so now it becomes the problem of estimating the width becomes the problem of doing an integral. So the integral is dp prime dq dk, a matrix element square, some matrix element square, and then the three and then two delta function. One delta function is like p sum over p, so p initial state minus p prime minus q minus k is equal to 0. The other is the conservation of energy. Let's say the energy of the initial state, let me call that E minus the energy of this P prime minus energy of Q minus energy of K, where by energy, let me call that epsilon of P is this construction. Okay, here actually I should be a little bit more careful with the hole because the energy of the hole is minus, but I'm going to do only order of magnitude estimate, but that is not very important. Okay, so here here's the Landau assume that this one is of order 1, that is, we cannot control the strength of the Coulomb or whatever interaction. So if the width goes to 0, it's not because m is small, it's because this integral over the phase space is small. Okay, let me show you how to estimate this integral. An integral where p runs only near the Fermi. So basically here we are interested in the region of phase of momenta near the Fermi surface like this. So a dp can be replaced by integral over the direction of p times the integral over the radial direction, which I call that d of epsilon p, because epsilon of p actually measure the radial magnitude of the vector p. And so this integral turns out to be integral over gamma is equal to integral over all this p prime hat, dq hat, dk hat, and then integral over the epsilon p prime, the epsilon q, the epsilon k, and then this delta function. But the delta function of momentum, very roughly, it's a delta function of pf times the hat, sum of the hat vector, so p prime plus q prime plus k prime, k minus the initial p, right? And then the energy is E minus epsilon p prime minus epsilon q minus epsilon k. And here, when we replace the delta function in momentum with this delta function, we say that the momentum mostly is the radial unit vector times pf, and the correction to that is small. So you see here, there are part of the integral that is of order 1. All these things can be estimated to give something of order 1. The thing that changes with the initial energy is in this integral of 3 energy times a delta function of energy, which is energy squared. Delta function is 1 over energy. And so that means that gamma is scaled like energy squared. Any question about this? So Landau theory, this picture of interacting quasi-particle is self-consistent. That is, if we assume this well-defined quasi-particle, then they interact through some vortex of interaction. Assuming that this interaction is short range, it can be modeled by some regular function of the momentum. In this estimate, will be replaced by some constant, and the energy dependence of the width is squared. That means as I go to lower and lower energy, the pole in particle propagator becomes closer and closer to the real axis. That is, this gamma becomes much smaller than E.
So you did pay attention to depends on the Fermi momentum and VF, so you have to fix the dimensions somehow.
Yeah.
But also VF is going to enter.
Mm-hmm. So all this going to sorry?
Is that E squared over the Fermi energy?
Or divided by the Fermi energy times some coupling constant square. But if the coupling constant of order 1, then it's just E squared divided by the Fermi energy. So
but why Fermi energy? Why Fermi energy is not an observable quantity in this theory?
it is. It appears in the matrix element of the interaction. So remember this one. Suppose I do some if I do some diagrammatic calculation, then this M, it's in the style of what people did in the 1950s. I would take this interaction and maybe improve it with some kind of a loop, etc. But roughly speaking, the strength of the interaction will be governed by this coupling constant E squared. Right? But then, from what I've said here, everything when A is of order AB in a normal matter, everything is of order 1. When measured in unit of Fermi length or Fermi energy or Fermi momentum, everything is of order 1. So this M then naturally will be of order 1 when we measure it in the unit of the Fermi energy.
Okay, but there were other things instead which are observable which you didn't keep track of, like Fermi velocity is an observable quantity, right? It can be renormalized. Fermi momentum also an observable quantity.
Can be also renormalized. Everything is assumed.
Fermi energy is the only thing which is not observable. Okay, it enters in some microscopics, whatever, and so and in the end result you're saying it's going to be Fermi energy.
Yeah. So roughly speaking, you have to say there is a Fermi momentum. This Fermi momentum actually is something that observable, right? And VF is something that observable. When I say Fermi energy here, is actually as rather say it has to be written as VF times PF.
Oh, okay.
Yeah, that would be, yeah. That's maybe confusing. Avoid the problem with ill-defined epsilon f.
A squared seems independent of the dimension.
It's independent of the dimension. Any dimension. Maybe except 1. I'm not sure if there is a subtlety with one dimension, but in any 2 or 3 dimension, one would get this E squared. Okay. Okay, so this is Landau theory. Not yet the Landau theory, but the very preliminary argument that led Landau to postulate that a state of a Fermi liquid can be, from the modern point of view, we should say that the low energy state of a Fermi liquid can be characterized by a distribution function f of x of p, which is occupation number of this like a number of fermions at point x that carries momentum p. So that in the ground state, so this is the quasi-particle. Strictly speaking, it's a very importantly quasi-particle distribution function. Distribution function of the quasi-particle, not the original electrons. So that the ground state corresponds to f equal f0 of x in p. x0 is a function of only p, and this f0 is equal to 1 if p is less than pf, and 0 if p is larger than pf. In terms of the quasi-particle, the ground state looks like a field Fermi sphere in momentum space with a sharp dividing surface called the Fermi surface. And the excited state, or let's say the ground state, can be thought of as described by a distribution function that is slightly different from the ground state distribution function. So this is the second assumption of Landau theory, that one can describe, and we will see why it's important. We can describe the excited state of a Fermi liquid in terms of a distribution function of quasi-particles.
How should I think about the phase of these particles?
How about the
Quantum mechanics. If it's very classical gas, yeah, there is just some distribution. But if you do quantum mechanics, there are various phase information about particles. So how is this encoded in this? How should I think about the phase, the quantum mechanical phase?
How do I actually don't know if one can formulate this question. Or maybe I should return to it later when we talk about limitations of Landau's theory. Clearly, there are some quantities that cannot be computed, and one of the quantity may be related to what the question you are raising. Okay, so Landau said that the energy there exists a notion. So here I'm rephrasing Landau a little bit in a way that slightly different from what presented in textbook, but basically it's the same. That there is an energy functional that is a functional of f, or let me call that Hamiltonian function of f, which can be expanded in power of delta f. So it is E0 plus integral. Now I'm going to integrate over x in p of some kind of epsilon p0 delta f of x in p plus 1/2. I'm going to write only two terms. So dp prime. Okay, so this, I'm not going to be f of p prime delta f of x p delta f x p prime. The standard Landau theory stop in the second order. This can be associated with the energy of a single particle carrying momentum p in isolation. So this is and this can be can be interpreted as the interaction energy that a particles at momentum p and a particle at momentum p prime would have. The interaction is assumed to be local in space because we are looking at the dynamics at wavelength that is much larger than the range of the interaction. So this is assumed to be Vf times P minus Pf. Okay, and Vf doesn't have to be equal to Pf over m, but it can be m star, where m star is typically different from m. The bare mass, it's a renormalized mass of the quasi-particle. And this is a phenomenological parameter. We would call them Wilson coefficients of the effective field theory that describe the Fermi liquid. The way that this formula is usually written in textbook is somewhere I put the...
Usually it's under the table.
Under the table. Yes, under this table. Oh, thank you.
Because it looks very unusual.
Yeah.
It's Japanese,
Thank you. That means it's good. Okay. Yeah, I have to put it somewhere here. Actually, we write the following formula. The energy of this is just another way to write this formula. The energy of a single particle, the epsilon over d f x in p, is the energy of, without this free energy, roughly speaking, integral over dp prime f x f p p prime delta f x p prime. And here you see that according to Landau, the modification due to the interaction between the what differs interacting Fermi liquid from the non-interacting Fermi liquid is the presence of this function that tell us that if there is a particle at the same place carrying momentum p prime, then it will change the dispersion relation of particle carrying momentum p of here. Now one may wonder why do we have to bother with this? This seems to be an expansion in power of delta f. If delta f is much smaller than 1, do we actually have, compared to f0, do we have to take into account the quadratic term? Can we ignore it with respect to this term? Or if we cannot ignore this quadratic term, why don't we have to continue? And the reason is that the reason why this quadratic term is important, is special, is that is the following. Let's imagine that we have a state that looks like a state at finite temperature. So I assume that I have a Fermi surface of quasi-particles, and then smear out, because I have finite temperature of order t. T is much smaller than epsilon f. Again, epsilon f is just Vf times Pf. Right. So then you can see that the contribution, this delta f, is of order t. Roughly speaking, that the width of the region where delta f differ from f is t. And so this integral is of order t square. Right? So basically, it comes from this delta p and p prime, both integral is concentrated in the shell with the width of order t. This t prime. Now, how about this one? This one actually is also t squared. And the reason is because its delta f integral is concentrated in the region of shell of order t. It's integral over p. But the bare energy of the quasi-particle also measured with respect to the Fermi energy. And so it's also of order t. So here this both term is of the same order of magnitude. This one is t, this both term is t squared. But if we go to the next term, it's of order t cubed. That is more. And so here you should start to see one feature of Landau theory that illustrates both the Landau's incredible intuition, and also it makes this Fermi liquid somewhat different from other systems. Is that somehow this term that we normally think of as interaction is not, even when we go to low energy, is not negligible compared to what we would usually call the free part. Okay, so we see this feature repeated in some other approaches.
It's like in the Wilson-Fisher fixed point. If you create epsilon, you have to keep a one-loop term.
Yeah, but here there is no epsilon. There is no 4 minus epsilon. Yeah, I mean there's no reason in this why. Well, there is a reason, but we can see it that Fermi liquid theory is somewhat special in the sense that this term that Landau should associate with the interaction between the quasi-particle is as important as the free part. Like this.
And the kernel F does not depend on P minus P prime?
The kernel F depends on the following. So in Landau's theory, we care only about F when P and P primes are close to the Fermi surface, because that's where delta F is non-zero. So F is a function of only 2 unit vectors. So let's assume the system to be like helium-3 isotropic. F is a function of only 2, actually a function of only one angle, theta, that is the angle between P and P prime. And this function of the angle can then be decomposed into sum over spherical harmonics. So I have PL cosine of theta. So this FL is called the Landau parameter. There is an infinite number of them, but in practice, only a finite number of them are substantially different from 1. In the case of helium-3, that is L equal to 0 or 1.
So does this interaction conserve momentum?
Okay, so let me go to the equation of motion and then discuss the conservation laws in the Landau's equation of motion. Landau's theory is formulated in terms of classical equation of motion. Although it describes a quantum liquid, Landau said we have to write down the following kinetic equation, d over dt. So if we have a system of fermions that in the initial state described by some distribution function, its evolution over time is given by the following equations. X dot df over dx plus p dot df over dp. Here's all these are vector product equal to 0, where x dot, we think about, so the picture that one can have is the following. We have a collection of these point particles moving in phase space, x and p, and evolution of the swarm of particle is described by a Liouville equation. X dot equal the epsilon p divided by p. Again, it's the epsilon 0 divided by p plus integral over p prime df p prime divided by p times delta epsilon p prime xp prime. Right, so I'm just emphasizing that this x dot is not trivial. It also depends on the distribution function, and p dot is equal to minus the epsilon p over the x dot over dx, and then here I will include an magnetic force acting on the quasi-particle. I assume that I assume that there is an external electromagnetic field coupled to the U1 charge. Like in the case of electron, this would be such as our usual electromagnetic field. The evolution of the system will follows this equation, where x dot has to be read out from the first equation. Yeah. So that's the content of Landau's theory. Basically, this means the following: that we can predict the behavior of the system in so question like response of the system to external electromagnetic field can be answered by solving this equation, classical equation of motion following this particle. Okay, so now I want to answer Julio's question about the conservation laws. So the following, one can check that the following quantity are conserved. So one can check that the total number of particles is conserved. One can check that the total momentum is conserved in the presence of, in the absence of external field. But in the presence of external field, the total momentum changes, becomes something like integral over dx rho of E plus J cross B, where rho and J's are the currents and the density and the currents associated with this particle in particular. Rho is just integral over P of F, so rho of X in P, and J equal to integral over P of X dot V of X in P. Just as we would expect from for any system coupled to electromagnetic field, the total energy is conserved. But the total energy here is just the Hamiltonian, so I'm not going to rewrite this Hamiltonian again.
So this is because of translation invariant
of F.
Of X.
The translation invariance of F, the F doesn't depend on X, implies the conservation of momentum. Yeah. And this, the fact that energy is conserved, it comes from some, this energy is not exactly conserved in the external field. One can show that it's the change of energy is equal to the ohmic heat, that is J dot E that appear. So the equation, the conservation equations are as one would expect.
What is funny is that why did you go straight to the description of complicated mixed states, finite temperature in terms of this in terms of this distribution function, why didn't you first
Look
not
at
describe just motion of individual excitations above the ground state? Let's just stay at zero temperature. Let's just shine, you know, a photon on this thing. You know, something's going to come out. Why? Well, you did discuss a little bit, you know, this decay of quasi-particles.
But if you look at Landau's treatment, this one somehow that's like the preface to all these basically classical equations that it's not based on any picture of individual like quasi-particle, but a description of a state, of a like a collective state.
If you say mixed state, you mean mixed state.
Doesn't have to be mixed. I'm going to tell you one feature now, since this question is raised. Let's try to answer the following question: what is the response of the ground state of our system to an external perturbation? Now, this clearly, if we have a state that is a pure state, and we subject that to evolution with external field, the state that we obtained should still remain a pure state. What is the feature of Landau's theory, Landau's description, that knows that the state that remains is the pure state? And the answer is the following. The equations that Landau wrote down here is a Liouville equation. Liouville equation conserve phase space volume. And so if we start our evolution with a state that has a very sharp Fermi surface, that is when F is either 1 or 0, then following the particle, if the surrounding of it has F equal to 1, it remains F equal to 1 all the time. Right? So the fact that the feature of the sharp Fermi surface is preserved under kinetic evolution. And so here, sometime in Landau's picture, one write expression for the entropy, that is dx dp minus np log minus fp log fp minus 1 minus fp log 1 minus fp. Sometime we don't have to use this formula, but S will be equal to 0 if the occupation number f of p can only be 0 or 1. Okay, so here's the interesting thing about Landau's theory. Somehow it's preserved in some sense the notion of the purity of a state. That the set of quantum states that are pure is in Landau theory correspond to a state that characterized by a sharp Fermi surface.
And we don't discuss angular momentum because we don't want to add explicitly.
Yeah, I was. Let me say the following things. That is, a feature of Landau theory is the classic one: conserve orbital angular momentum and spin separately. Yes. I think there must be a way to include the spin orbit coupling to Landau's Fermi liquid theory, and yeah, but I have not searched the literature for that. It's not. I haven't known. Another thing is that.
So there's like an F for spin up and an F for spin down, and they're not talking to each other.
There is an F that is the following. I think maybe there's two different F in Landau theory written for helium-3. There is a F symmetric, and there's a F, some kind of anti-symmetric F that is called sometimes G. And I forget. I think this is. This is the following. I can think about this. If this is but let me just say in helium-3 people don't need to think about in practice the spin orbit coupling. So spin is like an external index. So spin is conserved and orbital momentum is conserved. So yes. So so what do I want to say? So this Fermi surface the sharpness of the Fermi surface.
The shape of the Fermi surface will depend on x.
The shape of the Fermi surface would depend on x. So if I would draw a Fermi surface, say because I'm in two. So let's assume I have one axis correspond to x, right? One axis correspond to p. So let's imagine just a one-dimensional Fermi liquid. The Fermi surface in the beginning correspond to just two lines, and the region phase filled with electron would correspond to the region between these two lines. Suppose I subject the system to external field, then this will fluctuate like this. Right? Now, in higher dimension, the picture is similar, but it's harder to draw. I have some tube. Like if I think about 2 dimension, it would be a Fermi surface in 2 dimension, but extended in 2 other dimension. In a 4-dimensional phase space of x, y, of x. So this is px, py, but this direction would be like x and y direction. I would have a tube, and the shape of the tube can change. But the fact that it's sharp, the surface is sharp, would remains a feature if I start with initial condition when the surface is sharp. Okay, so now that's what do I want to say. I want to list complaints about the Fermi liquid theory that I would like to solve, and most of this complaint is not going to be solved in 3 lectures, but I think it's one included, well, our work that I'm sure has not solved all this problem. So one big issue with the Landau's Fermi liquid theory is that it's not improvable. It's like a lot of genius guesses by Landau and many other physicists. When one gets the answer, but one doesn't know how to improve it. The effective field theory is very nice. Effective field theory in the modern sense, in the Weinberg sense, are very nice because it's accessible to mortals. That is, we know the principle on which we have to operate. We have symmetry, we have the derivative expansion. We just need to work out all the possible terms that consistent with the symmetry, and then if we want to compute to higher order, sometimes we have to compute loop. There is some certainty with how to do loop and counter term, etc. But the procedure is very well defined. In Landau's theory, we have the final product, and it's not clear what this final product can be improved.
Is it true he just write down the answer?
He wrote down the answer based on physical picture. So it's there's a combination of theoretical insight and the insight from experiment that leads to this Landau's Fermi liquid theory.
But going back to Slava's question about the individual Fermi, I thought one can also formulate it as a theory of fermions, and then you see which interactions are relevant or irrelevant. There's this discussion by Polchinski.
Have you? Yeah. But if you read it, you would say there is no understanding, well, at least the way, after I have read it, And after I have read also other articles by Shankar and others, it left the question how to systematically improve it. You are presented with some complicated argument why this interaction should be included, but there is no understanding of what you miss, what is the order of magnitude of the correction that you missed, how do you systematically include them into the effective field theory. That not just left out.
Well, they just discussed there which terms are relevant. That in principle one can write the relevant terms.
In principle you can write it, but in practice it's not possible. If you read how the power counting in Polchinski, this power counting is, maybe I can come to this later. It's not a criticism of this Landau theory right now, but it's more like attempts to improve it, to make it more similar to effective field theory. Yeah. So this is one of these, and because there is no, it's not an effective field theory. We lose out a lot of things that we want to compute. For example, this is a effective. This is a classical equation of motion. In which sense is classical equation of motion capture the quantum dynamics? How do we compute loop correction to the result predicted by Landau? But maybe I would present to you one calculation by Landau using Landau's theory, show that it gives the correct answer, and then we can we can all appreciate that that it's not a it's a very non-trivial theory. So the calculation that I want to do is the calculation of two-point function of density. Very simple calculation. Density correlation function. I will outline how it can be done in Landau's theory, and then how it matches with the result that one would obtain in Feynman diagram. So density correlation. So the way that we would use Landau's theory to do that is through the linear response theory. That is, we say that if we turn on a source coupled to n, in this case is a source of A0 field coupled to n. So it basically take the Lagrangian A plus A0. Then we can compute then by looking at the expectation value of n at point x, we can get the retarded Green function of the density by the standard formula of linear response theory.
And now is integrated delta F?
It now is, according to Landau's theory, so this is a general formula, but by when we use Landau Fermi liquid theory to compute n, these n's have to be identified with integral of f over p.
The retarded propagator of which operator?
Of the n operator. So this retarded propagator is integral over is a t, well, it's a retarded propagator of n and n. So n x and y. Let me say that the nx and y commutator times theta of x0 minus y0. That's a retarded propagator of the operator n.
And the left-hand side, you're going to relate just as the volume of the Fermi surface at the point x.
So in the Landau theory, this is associated with integral over dp of f of x and p. And so if the Fermi surface is sharp, then it's just the volume of the field region at point x. Yeah.
So in what sense do you write commutators now? Because n is just the classic.
Okay, so this one is all in quantum theory. Yeah. And now Landau's told us that we can compute all this quantity, this right-hand side, by using a classical equation of motion. This is actually have to be operator. So this is the way one do in Landau theory, the way one would compute the retarded propagator is through solving the linearized equation written there. So let me linearize f. So f again is f0 plus f0 doesn't depend on x, depends only on p. It's a plus delta f. It's a just zero temperature step function. Delta f. The equation of motion becomes the following: d over dt times delta f plus and x dot. Okay, so x dot df over dx. Df over dx should be the delta f over dx because f0 doesn't depend on x, and times x dot. But x dot is in the linearized order. I can replace it with p of p, and now I introduce the following notation. This is the group velocity associated with the function epsilon p0. That is the energy of particle without taking into account influence of other particles. Okay, so the correction that I have in omit here or delta f square. So, and then I have to write this p dot. P dot is so if I have an external electric field acting on the system, that would be E dot d, but then I have to write it f0 over dp is equal 0 minus. Okay, so here I assume delta f is small and the electric field is small also because I'm doing linear response. Solving this equation, what did I omit? I think there's p dot plus. Yeah, I think I have to have plus. I have to check the sign in my note. I think it's plus. Yeah, plus. Okay, so here I'm sure this equation is correct if I ignore the Landau's parameter. So let's assume it's all Landau parameter.
Isn't the charge of the electron negative?
That might be the reason I put a minus, but it's yeah, that's p prime is equal to. So let's first do the calculation in the absence of interaction between quasi-particle. This would be calculation of a free Fermi gas. From that, I compute this delta f. It's better to do it in momentum space. So delta f is equal in momentum space is like something like omega minus v of p times q. Delta f of omega and q equal this, and then this E computed at omega and q, but E I replaced by q dot a naught, and then I have d f0 over dp. From that I find my, reading this formula, I find the retarded Green function up to some sign factor equal some constant factor equal to integral over dp, because I have to integrate this over p to get my total density. So I get q divided by omega minus b of p times q, and then I have to put what plus I epsilon to be pedantic, df0 over dp, something like this. Not going to compute this integral, but if I compute this integral, I get something like some power of the Fermi velocity times some functions, some dimensionless function, let me call just f, some dimensionless function of omega divided by bf, absolute value of q. Some dimensionless function that has both real and imaginary parts from this I epsilon, and I would have to compute this integral.
So the df naught dp localizes the integral to the Fermi surface?
Yes, it's like an integral over Fermi surface, because this one, you notice, this one is basically a delta function jump on the Fermi surface p, because this one is a step function, this one becomes a delta function, and the magnitude of the delta function is like a p hat or something times delta function minus. Yeah. It's an integral now, can be thought of as an integral over a sphere of some omega minus vf. It's something like integral over d theta, d phi, cosine theta, cosine phi, and then something with the 1 divided by omega minus vfq cosine theta, which then give rise to this function. So in 3 dimensions, it's on 2 dimensions, this integral can be taken. Now, this would be the prediction of Landau's theory, but the calculation this retarded Green function can also be calculated in free fermions by just a simple evolution of a one-loop diagram. This one-loop diagram here. Right. And this one-loop diagram, when one evaluate for small values of p and q, so it's p naught plus omega, p plus q, p naught p. One evaluate this Feynman diagram using the propagator of a particle in finite chemical potential. One obtains in the limit of omega and q much smaller than pf, in the limit when absolute value of the external momentum much smaller than pf, one obtains exactly this formula with no approximation be beyond ignoring higher ordering q terms. In particular, this is a non-analytic function, complicated non-analytic function, and the non-analyticity in this loop integral comes from the fact that here you have a particle hole pair. When we shine photons with momentum q, we create a particle and a hole pair that's separated by momentum q. All right, this is a photon coming in, create a particle hole pair, but this particle and hole, although they have relative momentum that is small, it can be anywhere on the Fermi surface. You can create it here. You can create on half of the Fermi surface. Right? You can create a particle here in a hole here. And so that's why this integral is, the Feynman diagram gives rise to this integral over the Fermi surface, just like the integral that we get in Landau's kinetic equation. But the non-trivial thing goes further. If we now have an interaction between the original particle, Landau's theory also makes a prediction and the prediction is different from what this would give to us, and it comes from the following terms. It comes from the fact that here we would have to have replaced E by E plus minus d epsilon p over dx. But epsilon p now depends on epsilon p0 plus something that linear in delta f, right, according to Landau's theory. Energy of a particle does not depend on itself, but also on the presence of other particles in at the same point. And so now the equations, solving this equation require us to know all these Landau's parameters. It can be done. Again, this calculation can be done. And we get a 2-point function of density.
What are you going to do now? Are you going to expand this Landau parameters, or can you?
So we get a result that looks like we have an integral, some kind of integral equation, because this one is some integral over dp prime. So we have an integral equation that one has to solve. In the 2-point function of density, probably I won't write down this integral equation, but I'm going to tell you what it corresponds to in the perturbation theory. In perturbation theory now, the set of, we turn on the interaction between particles, so we assume there's some interaction. And what we are interested in is the leading behavior of the density correlation function when the momentum is small. And it turned out by analyzing the diagram, one can show that one has to sum up a certain set of diagrams, like particles coming in like this, plus the diagrams that give rise to singular behavior are those that have in some kind of a intermediate cut a fermion bubble. So analyzing the Feynman diagram, first one show that there is a set of one can organize the sum of all these contribution to the well, density actually I have to then sew this together. I have to sum up the diagrams where there is a particle hole pairs in the intermediate state, and then one can show that this sum of the diagrams give rise to exactly the same integral equation that is obtained by Landau if one make a certain identification of the Landau's parameter. And the identification is the following. I'm just tell you this this little bit. So first we define. So this is diagrammatic. Identification of the Landau parameter. What does this Landau parameter of L correspond to? First, it's rather subtle. First, we define a set of 2pi irreducible diagram. Into 2pi in the sense that it doesn't have the particle hole cannot be cut in the S channel, so that there is 2pi in the S channel only, one of these channel. we define this function called this gamma. This is this vertex. This vertex is a function of p. Let's do this p prime, p prime, p plus q, p prime minus q. Right, this is a particle. Let me see whether I have it right. Particles whole 4-point vertex. If one if one neglect out the diagram with the loop, this vertex has a finite limit when q goes to 0. So when q goes to 0, it has this set of diagram can be shown to be regular in the limit q goes to 0. So define this gamma, and then we take the following resummation. We sum up the sorry, going through this in a way that may be not very coherent. We compute this loop diagram and select out the singular part. So there is a this loop diagram can be shown to be equal to some kind of VQ divided by omega minus Vp dot Q. P is the external momentum plus some regular part. Let's call that phi. I'm not sure I knows all the parameters that it depends on, but then we take this gamma plus gamma phi gamma plus gamma phi gamma etc. This phi is regular, and so this one regular means that regular in the limit omega goes to 0, q goes to 0. So this loop diagram is equal to some well-known singular part plus a regular part. Its regular part is there because the propagator may differ from the form it has near the Fermi surface, etc. And then we have to resum all this to make a gamma that is related in textbook, sometimes called gamma omega. And this one is the function of two parameters, p and p prime, that is directly proportional to the Landau's parameter. Okay. So this is Landau parameter. So, and the best place to read about this is in Abrikosov-Kakov-Zelashinsky, chapter 4. It's a chapter where one shows that all the one can reproduce many prediction of Landau's Fermi liquid theory. All these predictions are at the level of the linear response or two-point function of density or spin density, or all of that can be obtained by solving identical integral equation in the Landau's theory and in the resum perturbation theory. So here the proof of Landau, this is some kind of perturbative proof of Landau's Fermi liquid theory that is non-perturbative. Non-perturbative because it doesn't require that each of these vertex is small. One analyze the infrared behavior of certain class of diagrams directly in terms of the diagrams. I don't believe there is a proof that Landau's theory gives correct three-point functions, but I believe it's probably also possible. Okay, any question so far?
Always the retarded propagator.
No, the box here. Now the box here is a Feynman 4-point function, so it's all in the.
What is the loop?
This thing here
Yeah.
is sum of all possible diagram that one can write down that doesn't contains a.
So it's the exact propagator?
Exact 4-point, the exact sum of diagrams, a 4-point diagram that cannot be cut by cutting two internal lines.
But time order.
So
Time order.
One whole irreducible.
One particle, one whole. But it's not one particle, one whole irreducible in this channel. It's only in the other, in this channel. So it's not a standard 2pi, but it's standard 2pi in a certain, in one this channel. And these Feynman diagrams are all done in the standard technique with Feynman propagator. The matching here between Landau theory in this calculation requires one to match the retarded propagator with the Feynman propagator. But there's at the level of the 2-point function, it's a standard. Knowing the retarded propagator, one can reconstruct through it imaginary part the Feynman propagator and vice versa. Presumably, Landau's theory also gives us prediction for higher point function. For example, 3-point function. Well, to get the 3-point function, we have to solve the Landau equation to nonlinear order. First nonlinear order in the electric field, and get delta n as a function of E squared. And this would give us a retarded 3-point function, n. And so the retarded 4-point function, n, etc. But now there is one complaint about my complaint about Landau theory. It doesn't give us a way to compute propagator that cannot be related to the retarded Green function. So at the level, for example, a 4-point function, one has a out of time order correlation function, and Landau's theory doesn't contains a prescription to compute this 4-point function. It can predict all the 4-point function, and in principle, though, at that level of proof, haven't seen it. It in principle gives us the prediction for long distance and long time behavior of any point functions. I think.
Is that because we've thrown away the phase information or something like that? Like Slava was saying. I mean that
one can speculate. Yeah, that this more intricate information is beyond the information that the distribution function can capture. But I don't know the answer to that question because I don't know how to compute this 4-point function.
Since this is not, we are discussing some basically something which goes back to the Egyptians. It would be more surprising indeed if you could explain us why with more like ostensibly successful attempts, people wrote papers saying that they actually put things on effective theory basis like Polchinski.
People out
there who went on record saying that all fixed things, everything's now nice. So I think Landau never made any claims that he fixed anything, but those people did. So
it's
more surprising.
maybe in the beginning of next lecture I can spend some time telling you about Polchinski and Shankar and how they try to write down an effective field theory of this, and why in my view, this effective theory came short of the expectation of field theorists, I would say. Though there are some things that can be understood using Polchinski or Shankar's effective field theory formulations. Actually, I think come back to Belfato Galavotti, who was the first who try to write down this kind of effective field theory. The problem is here is the following, that the number of degrees of freedom in the Fermi liquid is very large compared to typical field theory. All the degrees of freedom near the Fermi surface are large, relevant. In Landau theory, one can see this in one dimension. One can parameterize the shape of the Fermi surface by two parameters, the upper and the lower range of the Fermi surface. But if we have a tube like this, it's an infinite number of parameters that one have to introduce in order to describe the shape of the Fermi surface. So that's a fundamental distinction, a fundamental difference between ordinary quantum field theory and the type of field theory that people try to write down in Fermi liquid theory. And all the difficulties with this effective field theory came from that.
But you are claiming you will remedy all that and
A little bit. You will see. Yeah, I will see this. The goal of this lecture is not to solve all this problem, because I don't have the solution to this problem. I can advertise the following. We know how to reformulate Landau's classical equation of motion in terms of an action principle. So this classical equation that looks quite complicated can be reformulated as an action principle. Now this action principle, we can try to take this action as the starting point to construct a field theory. And that's where additional problems appear, some of which we know how to solve and some we still don't know how to solve. So that's, yeah. Thank you.